All right, continuing on. In this example, we'll perform an analysis of variance using data from a Latin square design. Now this is example 4.1. Here's a description of the experiment. A ceramics engineer performed an experiment to test and compare the strengths of high tension insulators made from 4 new clay mixtures, which we'll denote by A, B, C, and D, and also a control, which we'll denote by E. She made 5 insulators from each mixture. She suspected that there was a temperature gradient from front to back and also from top to bottom in the oven. Because of this, she used a Latin square design with shelves, top to bottom, as rows, and positions on the shelves, that is front to back, as columns. After firing, the strength of each insulator was measured. The data, along with summary tables, are provided on the next 2 slides. So the question is, at least the initial question, is there sufficient evidence at the 0.05 level of significance to conclude that a difference exists in the mean strengths of the high tension insulators made from the different mixtures? And so here is the first table. Now this is not a summary table. This is contains the actual data. All right, and so the experiment was again performed according to a Latin square design. So we have 2 blocking factors called the rows and the columns. Now in this particular situation, the row blocking factor corresponds to the shelf from top to bottom in the oven, and the column blocking factor corresponds to the position on a particular shelf from front to back. All right, and so we see here that we've got the 5 levels for the row blocking factor, the 5 shelves, and then we have 5 positions from front to back on a given shelf. And in the cells, we have the strengths, the tensile strengths of these insulators. And in parentheses, after the response, we have the treatment or the particular type of insulator. All right, so let's look at the first summary table. And so here we have the first table, and in the body of the table, we still have the raw data, but we do not have the actual treatment for that particular cell. That's on the previous slide, but we've taken them out for the purposes of the summary table. And so this table summarizes the rows and also the columns. So we have the row summary values, the row sums over on the right-hand side. And we also have the column sums down along the bottom. And then because we will also need the uncorrected sum of squares, and in particular the total uncorrected sum of squares, we've got column sums of squares, uncorrected sum of squares for each of the columns. Now here is the second summary table, and this is a summary by treatment. So we have the sum of the observations for each of the treatments, along with the mean for each, the sample mean for each treatment. And finally, in the right-hand column, we have the overall sum, or the total sum of all observations in the experiment. And we also have the overall mean, or the mean of all of the observations in the experiment. Now, as a quality control check, we could go back here and look at this overall sum for all values in the experiment. And if we go back 1 table, we see that that matches up with the overall sum that we got in the previous table. So that gives us at least a little bit of a quality control check that we've summarized correctly. All right, so here we have the preliminary ANOVA table showing the degrees of freedom. All right, so we've got a Latin square design where we are comparing 5 treatments. And so we have a row blocking factor with 5 levels. We have to have a column blocking factor also with 5 levels. And then again, we have a treatment or a set of treatments with 5 levels. And the degrees of freedom for each of the row, column, and treatments would be P-1, 5-1, or 4 in this case. We've got 25 experimental units total, so we've got 25 minus 1 total degrees of freedom. And that leaves 12 degrees of freedom left over for error. All right, and so next we need to calculate the sums of squares for rows, the sums of squares for columns, treatments, and so forth. And so the first thing we'll do, as usual, is calculate the correction factor, the correction term, capital C. And this is the square of the overall total, the overall sum of the observations in the experiment, which you'll recall was 852.7. We square that, and then we divide by the total number of observations or experimental units in the experiment, which is P times P, or 25 in this case. And so the correction term is 29,083.8916, rounded to 4 decimal places. Next, the total sum of squares, the total corrected sum of squares, is given by the total uncorrected sum of squares minus the correction factor. All right, and so let me go back a few slides here. And here we have the total uncorrected sum of squares, 29,380.55. All right, and so that's here. We subtract off the correction term, and we get the total sum of squares, total corrected sum of squares of 296.6584. Next, we calculate the row sum of squares. And so this is going to be equal to, well, it's denoted by SSR, and it's equal to 1 over P times the sum of the squared row totals. All right. And so when we square the row totals, and let me go back here to the first summary table, what we need to do is we need to square each of these row totals and add those squared values up. And then once we do that, we divide by P, in this case 5. And then from that, we subtract the correction factor or correction term C. And so when we do that, the row sum of squares, or the sum of squares due to the row blocking factor, is 87.4024. Next, for the column sum of squares, we first add up the squared column totals. So again, let me go back to this first summary table. So we would square each of these values, add those squared values up. Okay, and then divide that sum of squared column totals by 5. And then from that, subtract the correction term, and we get the column sum of squares being equal to 16.5624. Now I just noticed that I had a little typo here. I had I as the index of summation here, but that needs to be J, and so I've corrected that. All right, so that'll be corrected in your notes. All right, and then next we calculate the treatment sum of squares, SST. And so to calculate this, we first square each of the treatment totals, then add those squared treatment totals up. All right, and so let's go back here to the second summary table. And so we would square each of these values. All right, add those squared values up. Once we do that, we divide by P, in this case 5. From that, we subtract the correction term, and that gives us the treatment sum of squares, which is 155.8944. And then once we have the total sum of squares, the sum of squares for rows, the sum of squares for columns, and the sum of squares for treatments, then we obtain the sum of squares error by subtracting from the total sum of squares the sum of the sum of squares for rows, the sum of squares for columns, and the sum of squares treatment. And so we get 36.7992 for the error sum of squares. And so now we can plug these values in. And so here I have the total sum of squares entered in. And then the row sum of squares, the column sum of squares, the treatment sum of squares, and then we get the error sum of squares by subtraction. Once we have those, we calculate the mean squares by dividing each of these sum of squares by the corresponding degrees of freedom. All right, and so we get 21.8506 for the row mean square, MSR. We get, let's see, 4.1406 for the MSC, the column mean square. 38.9736 for the treatment mean square. And then finally 3.0666 for the mean squared error. Once we have those, we obtain the F statistics by dividing a mean square for that row we divide that by the mean squared for error in this case. And so we get 7.1254 for the F statistic for rows, 1.3502, the F statistic for columns, and the F statistic for treatments, which is our primary focus right now, is 12.7091. Okay, so we've done the calculations, we've constructed the ANOVA table. What exactly is being tested? Well, we've got 5 treatments. These are, the treatment effect in this case is a fixed effect, right? These are the particular types of insulators, the particular compositions of the clay and all that the researcher is interested in. And so the treatments here represent a fixed effect. And so the null hypothesis is that the population treatment means are all equal. mu1, mu2, mu3, mu4, and mu5 are all equal. Now I suppose it would be better to denote these mu A, B, C, D, and E to correspond to the treatments, all right? And I suppose we could do that, but that might make things a little bit more cumbersome a little later on. So we'll just understand that when we say mu1, that corresponds to mu sub A, mu2 corresponds to mu sub B, mu3 is mu sub C, mu4 is mu sub D, and mu5 is mu sub E. All right, so these are the hypotheses that are actually being tested by the analysis of variance. All right, we'll use a significance level of 5%, 0.05. In this case, the critical point, and let's go back and look at the table. See, we've got, we're focusing on the significance of treatments here. We've got 4 numerator and 12 denominator degrees of freedom. All right, and so the upper fifth percentage point of that F distribution would be 3.26. Since the F statistic for treatments, F sub t, is 12.7091, which is greater than 3.26, based on that, we would reject the null hypothesis and conclude that differences do exist among the mean responses for the 5 treatments. Now, I would just point out that the p-value is fairly small, in this case 0.000284. All right, and so we see that we would reject the null hypothesis not only at the 5% significance level, but at the 0.01 level, the 0.001 level. In fact, any significance level that is greater than or equal to 0.000284. So a very significant result here, statistically at least. So because we have rejected the null hypothesis and concluded that differences do exist among the population treatment means, follow-up comparisons would be warranted. Now, let me show you how I obtain that p-value. All right, and so again, I used the TI-84 to get that. And so if we select the distribution functionality by pressing the second and then the vars key, that takes us to the distribution main menu. And then if we scroll down, we can select the CDF function for the F distribution. And we plug in as the lower endpoint the value of the test statistic, the upper endpoint positive infinity, and this is the best way to do that in this calculator. And then we enter the numerator and denominator degrees of freedom. All right, and then paste that, and that will paste that into the display window. All right, and then when we press enter, it does the invokes that function with those parameters, and so we get the p-value. And so you can see the value of this p-value to even greater precision than what I've provided on the previous slide. Now here is the ANOVA table that I've constructed using a spreadsheet. So I have a spreadsheet that I have constructed to perform these calculations. All right, and this does the calculations with a great degree of precision and accuracy. And so if you just go back and forth between this slide and this table that we showed previously, you'll see that we get the same values rounded to the decimal place is shown. Now, here is the SAS code that we could use to analyze this data. And because the length of the code exceeded the height of the slide, I've included it in two pieces. All right, and so the larger typeface here is the main thing I want to look at. But here we have the data step that I've used to input the data into SAS. And so you might, if you're not real familiar with SAS, you can look at this and see how to input the data. So I've got some housekeeping steps up here. All right, and then I create a temporary data set called set1 using the data step. And then I tell the data step or the data statement that I'm going to be inputting data. The variable names are row, column, treat, and then Y. And notice that I have a $sign after treat, TRT. That tells the data step that the third variable that I'm entering is a character. All right, and then I issue the cards statement. All right, and that tells SAS that what's coming next are the actual data. And then once I enter the data and complete that, I terminate that with a semicolon and then run. So once we have done that, we have a temporary data set called set1 that we can then use to perform analyses on it. So then I have proc mixed. I'm invoking proc mixed here. And I'm telling it the data set that I want to analyze is set1. And as we've been doing when we've used proc mixed in the context of these analyses, I'm issuing the method equal type 3 option so that we can, that will cause proc mixed to do the same kind of analysis, the same calculations that we're doing, and it will also display the results in an ANOVA table style format. If we don't issue the method equal type 3 option, then what SAS will do is it will use the default method, which is maximum likelihood, or actually it may be REML, but the calculations will not be the same method of calculation, although in many cases the results will be the same. But if you don't issue the method equal type 3 option, then it won't produce that ANOVA table. All right, and so but I wanted to have that ANOVA table so that we can compare with what we've done by hand. Okay, so then we have the class statement. This statement is used to identify the classification variables in our data set that we'll be using in the analysis. And so we have the row variable, the column variable, and the treatment variable are all classification variables that SAS will need to construct dummy variables for. Then we issue the model statement. The response variable is on the left-hand side of the equal sign, that's Y. And then the explanatory variables in the model show up on the right-hand side. And we only have, and let me just be more specific about that, the fixed effect explanatory variables. And we have only one fixed effect explanatory variable, and that is the treatment variable. And then we also need to issue the option DDFM equal Satterth weight. All right, and there are other options as well for this. There's the Kenward-Rogers and so forth, but we're using this because this is one of the methods that we've looked at for approximating degrees of freedom when that becomes necessary. If you don't have this, if you just terminate that model statement with a colon, then in those situations where we know that we need to approximate the degrees of freedom, SAS won't do that. All right, so we need this here in order to tell SAS to go ahead and use an approximation method, and in particular the Satterth weight approximation method, to estimate those degrees of freedom. Now, think back to when we did the randomized complete block design. We had one random effect, one blocking effect, and that blocking effect had to be in the class statement, right, because it is a classification variable. And it also showed up in the random statement. That's how we told ProcMixed what the blocking factor was. Now, in this case, with the Latin square design, we have two blocking factors essentially, and they are called, in this data set, row and column. Now, in another data set, they may be called something else. It doesn't really matter what they're called. We need to understand what they are. All right, and so we know that in this case, the two blocking factors associated with this Latin square design are called row and column, so we include those here. All right, so this will give SAS the proper instructions so that it will do the corrected analysis. Now, SAS will do an analysis, all right, regardless of what you put in here, and as long as you haven't done something that's going to cause an error. But in order to get a correct analysis, we have to make sure that we input the correct model, the correct random statement, and we correctly specify the variables in the class statement in order to get an analysis that is appropriate for this particular Latin square design. And so when we do that, this is the ANOVA table part of the output that we get. And so if you go back and compare this with the results that we got from the spreadsheet calculation or that we did by hand, then you'll see that we get the same values. Okay, so this is how you do the analysis for an ANOVA using data from a Latin square design. And we see the specific hypotheses that are being tested in that context. And so we'll stop this lecture video and we'll pick up in the next lecture video with the next topic.